Before we move on in Chapter 8, we have to go back and pick up a section in Chapter 5 called Indeterminate Forms and L'Hopital's Rule. First of all, notice it's not La Hospital, there's no S there, L'Hopital's Rule. And we start with actually the theorem that states L'Hopital's Rule. Let f and g be differentiable functions on an open interval AB containing C, except possibly at C itself. Okay, let's stop there. So f and g have to be differentiable, meaning you can take a derivative on an open interval containing C, except possibly at C. Okay, so, suppose you had a function, f or g, that had a sharp corner, like that. Right? We know that a function's not differentiable at a sharp corner. Suppose that's at C. What this is saying is, if this were function f or g, there's some open interval around C for which the function is differentiable except for at C, possibly. So notice, near C, the function is differentiable. It's just at C, it's not. Let me change this up. Suppose I put in another, sharp corner somewhere, like that. And again, is there an interval around here for which the functions are differentiable, f or g? Yes, right? The function's not differentiable there either, but you can pick a tiny open interval. So, we're nearby the point that we're not differentiable. Everything else has to be differentiable. All right? And the second part says, and assume that the derivative of g is not zero for all x in AB except possibly at C itself. Okay? So again, what would it mean for the derivative of g to be zero? Right. Okay. And so again, here's C. Again, derivative not zero except possibly at C. So suppose you had a function that did this. Right. Notice at C, that's a minimum. The derivative is zero. But nearby, notice the derivative is zero here and here, but you can find a tiny interval around C for which everywhere else the derivative isn't zero. At C, the derivative is zero, but everywhere else it's not. So that's the idea. So when you're near C, you can take an interval small enough where the only place the function is not differentiable for f and g is at C, and the only place g is the derivative is equal to zero is at C. Okay, so if you can find a tiny enough interval, that's the only place where the derivative is equal to zero or not differentiable, then we're okay. Okay, now what does L'Hopital's rule say? Right, it says if you're taking the limit as x approaches C, C is some number of a quotient f and g. Again, so neither function, both functions have to be differentiable around C except for possibly at C, and the function g, the derivative near C cannot be zero except for at C. So if this is the case, okay, then what do? If you take the limit of the numerator and get zero, and you take the limit of the denominator and get zero, that's called the 0, indeterminate form. Remember, 0 over 0 is undefined. That doesn't mean the answer is undefined. Right? We saw that in Calc 1. Just because you get a 0 over 0 doesn't mean the limit's undefined. You may have to do some algebra. Or if you take the limit of the numerator and get plus or minus infinity, and take the limit of the denominator and get plus or minus infinity, that's this particular indeterminate form. Again, infinity over infinity is not 1. Okay, so if you get either one of these, well, I guess there's 4 choices here, any one of these 5 forms, L'Hopital's rule says the limit of this quotient is the limit of the derivative of the numerator divided by the derivative of the denominator. Now I'm not taking the derivative of the function because you'd have to use quotient rule. It's derivative of the top over derivative of the bottom. And then you check again, can you compute this limit? The whole idea is if this limit's hard to compute, if it satisfies the conditions on the functions and it's one of these indeterminate forms, the limit of this is the same as the limit of this, and then maybe this one you can do. Okay. Now the result, it's also true, x doesn't just have to go to C, x can go to plus or minus infinity if you get one of these forms, 0, 0, infinity over infinity. And then also, L'Hopital's rule applies if you have any of these indeterminate forms. 0 times infinity, so you have a product of two functions, the limit of the first is 0, the limit of the second is infinity. Or you get 1 to infinity, so you have an exponential situation. The limit of the base is 1, but the limit of the exponent's infinity. 0 to the 0, same sort of idea, or an infinity minus infinity. Infinity minus infinity is not 0, infinity is not a number. Now typically what do you do? If you have an indeterminate form that's one of those, you can manipulate the function, rewrite it in such a way that it turns into one of these. That's the idea. So if you get one of these, you try to rewrite it like this, and then use the original L'Hopital's rule. Let's do an example. Okay, it says find the limit as x approaches 1 of this rational function. Now remember, when you learned in Calc 1, to take the limit of a rational function as x approaches a constant, you try to plug in first. If I plug in, I'll get 1 plus 4 minus 2 minus 12 plus 9. That's 5, that's 3, that's 0. And if I do the same thing in the denominator, I get 1 minus 6 plus 13 minus 12 plus 4. That's 18 minus 18 is 0. So notice, this is, I got a 0 for that limit, a 0 for that limit. That's a 0 over 0 form. Now remember what you did in Calc 1. When you plug a constant into a polynomial and get 0, that means x minus that number is a factor. So I can factor an x minus 1 out of the numerator and x minus 1 out of the denominator and cancel and try again. But now that we have L'Hopital's rule, I know that this limit, the limit as x approaches 1 of that rational function, is the same as the limit as x approaches 1 of the derivative of the numerator over the derivative of the denominator. Sorry. 4x minus 18 squared plus 26x minus 12. Okay. And now I caution you, treat this as a completely new problem. How do you take the limit of a rational function? You try plugging in 1. I get 16 minus 16, and then I get 30 minus 30. It's a 0 over 0 form again, so I can use L'Hopital's rule again. In fact, I would highly recommend, say in your notes, you don't have to do it on a test, but I mean, make a little note that you're using L'Hopital's rule, so when you look back at it, you'll know what you did. You're not going to remember, 3 weeks from now what you did. So I can use L'Hopital's rule again, keep writing limit sign until you actually take the limit. So the limit of this is the limit of the derivative of the numerator, 12x squared plus 24x minus 4, over the limit of the denominator, that's a derivative of the denominator, 12x squared minus 36x plus 26. 12x squared, 24x minus 4, 12x squared, okay. And now treat it as a new problem. How do you take the limit of a rational function? You try by plugging in 1. And notice here, I don't get a 0 on the denominator. You can't use L'Hopital's rule now. Okay? So now we just plug in, so I don't have to write limit because I'm plugging in. I get 12 and 24 minus 4, what is that, 30, 36, 32. And the denominator, it looks like I get 2. So the limit's 16. Okay? You can't just do L'Hopital's rule indefinitely here. I mean, you keep going. Every step you have to check and see if you can apply L'Hopital's rule again. Eventually, here, this is not a 0 over 0 form or an infinity over infinity form. This is one you could have taken the limit of Calc 1. You plug in 1. Okay, so don't just keep taking derivatives because you feel like it. Okay, let's do another example. Okay, the next example is number 19. It says, take the limit as x approaches 0 from the right of e to the x minus 1 plus x all over x squared. X cubed. Okay. Okay. And I didn't check the conditions on the f and the g, but about the nearby, the derivative isn't 0 for the denominator, and polynomials aren't a problem. Notice I have a polynomial here too. That's going to satisfy the condition, as will e to the x and another polynomial. Right? So if I just try to plug in 0, notice in the denominator I get 0. E to the 0 is 1 minus 1 is 0. This is a 0 over 0 form. And in the paragraph at the beginning of the page, it also, if L'Hopital's rule applies for two-sided limits, it makes sense it would apply for one-sided, so we're good. Okay, so I'm going to use L'Hopital's rule here. Keep writing limit until we actually take the limit. So the derivative of the denominator is 3x squared, no problem. And the derivative of e to the x is e to the x. And the derivative of 1 plus x is 1. So the derivative of negative 1 is 0, the derivative of negative x is negative 1. Okay, same sort of situation. If I try plugging 0, I get e to the 0 is 1 minus 1 is 0 over 0. It's 0 over 0 form again. I can use L'Hopital's rule again. The derivative of e to the x is e to the x, and the derivative of 3x squared is 6x. Again, treat it as a new problem. When you take the limit as x approaches 0, if you plug 0 in the numerator, you get a 1, and you get a 0 in the denominator. 1 over 0 is not one of the indeterminate forms. You cannot use L'Hopital's rule here. Now you just have to think about it. When x gets close to 0, e to the x is getting close to 1. When x approaches 0 from the right, you're plugging in tiny, tiny, tiny positive numbers, 0.00001. The denominator is tiny, tiny, but positive. So you have 1 divided by a tiny, tiny positive number. That's going to get huge. So the answer is infinity. Notice if x had been going to minus infinity, the numerator be getting close to 1, the denominator would be getting close to 0 from the left, like negative 0.00001, and that would have been minus infinity. So the reason why they did the one-sided is so you'd either get an infinity. X is approaching 0 from the left, you get negative infinity. If this had been a two-sided limit, the answer would have been does not exist, because one side's infinity, the other side's minus infinity. Okay, the next example is really a problem from Calc 1. And we have to recall a limit. Let me recall a limit from Calc 1. The limit as x approaches 0 of sine x over x was 1. Hopefully you remember that result. Okay, so when x gets close to 0, the limit of sine x over x is 1. Now, be careful, you don't just have to have an x here. As long as these two expressions are the same and they both go to 0, then the limit turns out to be 1. So you don't just have to have an x there. I mean, for example, if I had the limit as x approaches 0 of sine of 4x cubed over 4x cubed, right? So I have sine of 4x cubed at 4x cubed, right? They're both 4x cubes, and when x goes to 0, both of those go to 0. So it fits this form, and that answer would also be 1. Okay, so it doesn't have to just be an x. Okay? Okay, so that's the result I want to use here. So it says evaluate this limit without using L'Hopital's rule. So I want the limit as x approaches 0 of sine of ax over sine of bx. I mean, when I teach Calc 1, I do this example. And assume a and b are not 0, because if a and b are 0, you just get 0 over 0, which doesn't make any sense. Okay. So going back to what I was just talking about, again, I'm not using L'Hopital's rule. Notice if you plug in 0, you'll get a 0 over 0 form. But I want to use the thing we just talked about. I have the limit of sine of ax. If I could get sine of ax over ax, it would fit that form. So that's what I want to do. So I want sine, this is what I want, sine of ax over ax. Right? That's what I want up in the numerator, because then it fits the theorem and I can take the limit. But I can't just throw in ax because I want to. You have to balance out. So if I put it in here, I have to multiply it by it out here, right? So they'll cancel and I'll still get sine of ax. I haven't changed the function in the numerator, I've just changed the appearance. Likewise, I want to do the same thing in the denominator. So I get sine bx over bx, but I just can't throw in a bx because I want to, so I need to multiply the denominator by bx as well. So notice if I cancel the ax's, cancel the bx's, I have my original problem. Okay, and notice, I mean, I didn't really have to put the x's because they wind up canceling anyway, right? So I really just have a over b out there. But notice this limit, it's sine of, the ax's match, and when x goes to 0, they both go, ax's go to 0, so that turns out to be 1 for the limit. Same argument here, that limit is 1. Again, the x's really cancel here. When x goes to 0, I just have the limit of a constant, which is a over b. And that's the answer. So again, you don't need L'Hopital's rule in this particular problem. But the next example says, well, let's do it with L'Hopital's rule. Let's do the problem again. Limit as x approaches 0 of sine ax over sine bx. Again, we can use L'Hopital's rule because if I tried to take the limit by plugging in, you get 0 over 0. That's an indeterminate form, and it fits the forms we can use L'Hopital's rule with. So limit as x approaches 0. So we take the derivative of the numerator, the derivative of sine of ax is cosine ax times a, you have to use chain rule, and the derivative of sine of bx is cosine bx times b. Well, notice the issue in the original problem was we had the sine function. If you plug in 0, you'll get sine of 0 over sine of 0, which is 0 over 0. Now we have cosine. Cosine of 0 is 1. So you get a cosine of 0, cosine 0, that's 1, they cancel, and you just get it's a times 1 over b times 1, which is a over b. So you don't have to do any of this, you don't have to refer back to that previous limit I mentioned, limit as x approaches 0, sine x over x. You don't have to do this manipulation to get it to match that original theorem. You just use L'Hopital's rule and it pops right on out. No problem. Okay, the next example, number 60 says, let's do the limit as x approaches 0 from the right of 10 over x minus 3 over x squared. Okay, first it says identify the type of indeterminate form given by the limit, then evaluate the limit. Okay, so first they want us to tell what type of indeterminate form this is. So if you took the limit of the first term and then took the limit of the second term, what indeterminate form do you get? Well, when x approaches 0 from the right, you know, x is like 0.00001, 10 divided by that is getting big. So this is an infinity. And same thing here, right? When x approaches 0 from the right, the denominator is tiny, tiny, 3 divided by that would be huge. So the indeterminate form here, the indeterminate form is infinity minus infinity. Don't write equals infinity minus, I know the book is doing that sometimes to identify the form, but that just doesn't make any sense. I typically won't ask you for the form anyway. You should recognize what type of form it is. So as I mentioned at the beginning, this doesn't fit the L'Hopital's rule 0 over 0, infinity over infinity. But oftentimes, you know, the 0 to the 0, the 1 to the infinity, and infinity minus infinity, you can rewrite the function so it fits L'Hopital's rule. In particular, I think what I would try here is just get a common denominator. Right? Just combine them into a single fraction. Notice the least common denominator is x squared. So I need to multiply the first fraction by x over x. So if I do that, I get 10x minus 3 over x squared. That still doesn't fit L'Hopital's rule, does it? But that's okay. Right, multiply by x over x, you'll get 10x over x squared, combine the fractions. Okay, so notice it doesn't say use L'Hopital's rule to find the limit. It says evaluate the limit. I just assumed it was going to be a L'Hopital's rule problem. But notice when I combine these together, if I try to plug in 0, I get negative 3 over 0. Now again, you can't say undefined, right? I mean, you actually have to think about what's going on. So the numerator is getting close to negative 3. And the denominator, again, when we approach 0 from the right, we actually never get to 0. So it's like 0.00001 squared. So you've got negative 3 divided by a tiny, tiny, tiny number, which is going to go to negative infinity. So this was not a L'Hopital's rule problem. I just assumed it was going to be. Again, be careful, like I mentioned in class. Sometimes I have these red herring problems in the section. Just because it's this problem in the section does not mean it's going to use L'Hopital's rule. This one I didn't use it at all, the way I solved it. So got a common denominator. Notice the numerator, when x goes to 0, the numerator goes to negative 3 and the denominator goes to 0. That's not one of those indeterminate forms. So you argue the numerator gets close to negative 3, the denominator is tiny, tiny. So negative 3 divided by a tiny, tiny number is it's gonna blow up but be really negative. So the answer is minus infinity. I didn't need L'Hopital's rule. Okay, let's look at the next one. It specifically says evaluate without L'Hopital's rule. I did a problem like this in Calc 1. It says limit as x goes to infinity of x squared over the square root of x squared plus 1. Okay, just to backtrack for a second before I do that problem. We talked about how to take the limit of a rational function when x is approaching a constant. Remember, if you have x going to plus or minus infinity of a rational function, yeah, I'm just making this up. Right, something like this. I mean, you can look at the little black box, or the blue box, or the gray box they put in the section and memorize, but I want you to understand a concept here. So when you're taking the limit of a rational function when x goes to plus or minus infinity, if you want to understand what's going on, you look at the highest power of x in the denominator. You'll see some books say take the highest power of x anywhere, but in certain cases it falls apart, so I don't know why they tell you to do that. Take the highest power of x in the denominator, and then divide every term by that highest power. So basically what I'm saying is multiply by 1 over x cubed over 1 over x cubed, highest power in the denominator. So I'm going to divide every term up here by x cubed, every term in the denominator by x cubed. So let's see what we get. 3x cubed over x cubed is 3. 2x squared divided by x cubed is 2 over x if you simplify. And you get 6 over x cubed. Same thing down here, 5x cubed over x cubed is 5. X over x cubed is 1 over x squared, and you get minus 2 over x cubed. Now I know I made the function look worse, but I did this for a reason, because if you can't plug in infinity, oh, it's huge over huge, and that doesn't make any sense, right? But look at this. When x goes to infinity, 2 divided by x, 2 over 10, 2 over 100, 2 over 1,000, 2 over a trillion, that goes to 0. That goes to 0, that goes to 0, and that goes to 0. And constants stay the same. So you get 3 plus 0 plus 0 over 5 plus 0 plus 0. Okay, so when I'm taking the limit as x goes to plus or minus infinity of a rational function, I divide every term by the highest power of x in the denominator, and then you can see which terms go to 0 if they look like this, and then you've got your answer. Notice if I said x went to minus infinity, where there's no difference because each of these still go to 0. Okay, so that's why it works. Okay, now with that in mind, let me try to do this problem. Okay, so it's not a rational function, but when x gets huge, this plus 1 is kind of negligible, and so the root x, you have a root x squared, okay, which you could simplify down to a polynomial. Okay, so if I ignore the plus 1 and think of that as root x squared, it's the square root of a quadratic. I think of this as being linear. Okay, so the square root of an x squared, I think of it as just being linear. So when I said divide by the highest power of x of the denominator in the problem we just did, I know the highest power of x is showing up as x squared, but I'm taking the square root of it, so I'm going to think of it as x. So what I want to do is divide every term by x. Okay, so I'm following the model of the procedure we just did. See, there's not going to be a black box in the book saying, oh, the answer is so-and-so on a problem like this or others. So that's why I went through that, so you understand the logic, the procedure. You can modify it to this problem. So let's take the limit as x goes to infinity. Well, x squared divided by x is x, and the denominator, I'm just going to leave it like this for now. Okay, so x squared over x is x, and then I have the root divided by x. Now the way this is written, I can't really do any algebra on that. But if you have a square root of something over the square root of something, that's the square root of the quotient, right? So if I could rewrite x as a square root, I'd have a root over a root, and I could do some algebra on it. Now remember in our discussions in previous classes, we discussed the square root of x squared, and we said that was the absolute value of x, right? And notice if x is non-negative, if x is greater than or equal to 0, absolute value of x is x, and if x is less than 0, the absolute value of x is negative x. Because if x is negative, the negative of the negative would be positive. So remember we went through that before. So I want to replace x with the square root. Now is it legal here, because we have to be careful, can I rewrite x as square root of x squared? Is that the same thing? Remember, the square root of x squared in general is the absolute value of x. However, we're assuming x is going to infinity. So x is blowing up. Eventually x is going to be positive. And so the square root of x squared is x, right? When x is positive or non-negative, the square root of x squared is x. So I can replace x with square root of x squared. So it's perfectly fine here. Okay, let me continue over here. So then I get x over, I have a root over a root, so I can write that as the square root of the quotient, x squared plus 1 over x squared. That's why I did that. I rewrote x as square root of x squared to get a root over a root, but a root over a root is a root of the quotient. Now, we're almost done. Under the radical, I have a rational function with a single term in the denominator. Oftentimes when I have a single term in the denominator, I break up the fraction. So that's what I'm going to do here. X squared over x squared is 1, and then 1 over x squared is 1 over x squared. Again, the whole idea is to make it look like this, like the example, the rational function I did, divide by the highest power of x in the denominator. We got things that look like that. Now when x goes to infinity, what happens to this? Well, when x goes to infinity, right, 1 over x squared goes to 0, and then you have 1 plus 0, square root of 1 is 1, and in the numerator x is blowing up, so it looks like that's going to infinity. Okay? Again, the denominator is going to 1, but the numerator is blowing up. Okay, then it says, right, then it says do it with L'Hopital's rule. So I did the problem without L'Hopital's rule, now it says do it with L'Hopital's rule. So I'll come back over here. Okay, so now we're doing the problem again. Now let's convince ourselves we can use L'Hopital's rule. When x goes to infinity, the numerator blows up, goes to infinity. When x goes to infinity, the denominator, you get a large number squared plus 1. That's huge. The square root of it's still going to be huge. So this is an infinity over infinity form, so we can use L'Hopital's rule. Right? So it's the derivative of the top over the derivative of the bottom. The derivative of x squared is 2x. Now, again, think of the denominator as x squared plus 1 all to the 1/2 power. What's the derivative of that? Bring down the power, leave the stuff alone, subtract 1 from the power is 1/2 power, so minus 1/2 times the derivative of the stuff. I have to use chain rule. Again, I'm thinking of square root of x squared plus 1 as x squared plus 1 to the 1/2. So the derivative is bring down the power, leave the stuff alone, subtract 1 from the power, times the derivative of the stuff, 2x. Okay, let's simplify. The 2x's cancel. 1 divided by 1/2 is 2. And then x squared plus 1 to the negative 1. I have negative exponent means reciprocal, so it goes in the numerator. I get square root of x squared plus 1. And when x goes to infinity, you see that blows up. And that's the answer we got over here. So this was without L'Hopital's rule, and that was with. This just shows you can do a lot of problems without L'Hopital's rule. But notice that was a little shorter. We didn't have to play all the games with the algebra. Okay, 2 more to go. Okay, the next example says identify the type of indeterminate form and then find the limit. So we want the limit as x goes to infinity of x tangent 1 over x. Okay. When x goes to infinity, x blows up. So that's an infinity. And when x goes to infinity, 1 over x goes to 0. Sorry. When x goes to infinity, 1 over x goes to 0, and tan of 0 is 0. So the indeterminate form here is 0 times infinity. Again, that is not 0. See, this is blowing up, that's getting tiny. But if you have a huge number times a tiny number, that doesn't mean you're going to get 0, right? I mean, you realize this term is never 0. Right? Tan of 1 over 1,000 is a non-zero number. Tan over 1 over a billion is a non-zero number. So you can't get 0 out of the product. Now the product can head to 0. If this is getting close to 0 faster than that's blowing up, the limit could go to 0. Okay, so that's an infinity times 0 form. Now it doesn't fit the L'Hopital's rule form, but perhaps we can rewrite the function to make it look that way. Now there's only a finite number of things here. First of all, realize L'Hopital's rule is talking about quotients. So it would make sense to write this as some kind of quotient. And it still may not be obvious how to do that. But remember the theorem we had a little while ago that I reviewed from Calc 1, this one. Limit as x goes to 0 of sine x over x is 1. Notice the key was getting the same angle here and here. Notice the angle in this problem is 1 over x. Notice it's not sine, I understand that. But the angle here is 1 over x. So if I had a 1 over x and I had a 1 over x here, maybe there's a similar result for tangent, and there is. So I'm going to rewrite this function as that. Right? To divide by 1 over x, you invert multiply, you get the original function. So my motivating idea of going from here to here is this, even though it's not sine. Right? Now, when x goes to infinity, what do we have here? Right? 1 over x goes to 0, tan of 0, 0. This is a 0. 1 over x goes to 0. Now it's a 0 over 0 form, and I can use L'Hopital's rule. Okay, so the whole thing was, this was a product, and for L'Hopital's rule, we need a quotient. So it either made sense to either put that in the denominator or put that in the denominator. I mean, we could have said x over cotan of 1 over x, couldn't we? If we had done that, let me see, the numerator would be going to infinity, and the denominator would be going to infinity as well. That'd be an infinity over infinity, and this is 0 over 0. So again, I haven't worked it out. I mean, I have to work out to make sure it's okay, but it seems okay so far. Okay, let's continue with this one now. So we can use L'Hopital's rule because this is 0 over 0 form. Notice here I just rewrote. I didn't put L'Hopital's rule here. I didn't use L'Hopital's. So the limit as x approaches infinity, it's the derivative of the numerator. The derivative of tangent of stuff is not tan. The derivative of tangent of stuff is secant squared of stuff, right, times the derivative of the stuff. Now this is x to the minus 1, so the derivative is minus x to the minus 2. But let me do that again. The derivative of tangent stuff is secant squared stuff times the derivative of the stuff. This is x to the minus 1, so the derivative is minus x to the minus 2. And likewise, the derivative of 1 over x is minus x to the minus 2. So if you do the cancel, notice these are the same things, so they cancel. And I'm left with the limit as x approaches infinity of the secant squared term. But when x goes to infinity, 1 over x heads to 0, and secant squared of 0 is 1. And it pops right on out. So the theorem we had for sine is also true for what I say. All right, let me see. Suppose I had tan of x over x instead of sine of x over x, right? So I'm making a new theorem like we had for sine. So if you notice you can use L'Hopital's rule on this, because tan of 0, 0, and 0, and 0 is tan of 0, 0 over 0. That's 0 over 0 form. Use L'Hopital's rule. The derivative of tangent is secant squared x. The derivative of x is 1, right? And when x goes to 0, secant of 0 is 1. So the result that we had for sine, the theorem is also true if you put tangent there. Now it's not true for cosine. The key is that tangent and sine of zeros is 0. Okay? Okay. So knowing that theorem, you could have jumped from here to here. When x goes to infinity, it's the same angle. When x goes to infinity, that goes to 0, that goes to 0. Now that I know that theorem, we could have jumped down to 1. But that's fine. Okay, then this last example, it says, find the limit as x approaches 0 from the right of e to the x plus x to the 2 over x. Wow. It says identify the type of indeterminate form and then evaluate the limit. Okay, so if x goes to 0, what type of form do we have? When x goes to 0, e to the x, e to the 0 is 1 plus 0 is 1. So the inside the parentheses is heading to 1. But 2 over, when x goes to 0 from the right, so you got 2 divided by a tiny, tiny number, that's huge. So this is a 1 to the infinity form. Now you can't say that's 1, right? Because like I said before, I mean, this number is not equal to 1. It's 1 plus a tiny number. So that's not 1. So this is getting close to 1, but it's not equal to 1. And the denominator is getting huge. So Yeah, so you can't say it's 1. Just from saying, oh, that's 1 to the 1 to the anything is 1. First of all, infinity's not a number. Okay, so that's the indeterminate form. So again, I mean, the paragraph at the very beginning of the section said 1 to the infinity forms you can rearrange to get L'Hopital's rule. So what I'm going to do here, let me call this y, right? So my next step now, I'm going to call this y. Okay, fine. Now what's the issue here? The issue here is I have variables in the base and variables in the exponent. Do you remember in Calc 1 when you had a function like that, you know, variables to the variables, and it said find the derivative? Do you remember what you did to do that? When you had variables to the variables. If you have variable to a number power, we knew the derivative, bring down the power, leave the x alone, subtracting them from the power. If you had a number to the variable power, that was an exponential function. We learned how to take derivatives of those. But if you had a variable to a variable, we didn't have a formula for that, but what'd you do? Do you remember? That was a process called logarithmic differentiation. We took log of both sides, right? Take log of both sides. Then you have log of something to the power, you can bring the power down. Then you don't have variables to the variables anymore, you have a product. That's what we're going to do in this particular problem. I have variables to the variables, and we don't have any limit results on stuff like that. So I'm going to take natural log of both sides. Taking natural log of both sides. Okay, now, log is a continuous function where it's defined, just natural log of x. And certainly this is defined when x is positive, right? No problem. And so, but when you have continuous functions, you can move the limits inside and out. So I'm going to go ahead and do that. So I'm taking the limit on the outside. I'm just moving it to the outside. I'm putting a log in here. Okay, now it's just like what I said before with the x to the x. I have log of variables to the variables. Using the log properties now, I can bring the 2x down front in front of the log. Let me see, do I want to? Yeah, let me write it as a quotient. So I'm going to bring the 2x down, but I'm going to write it as a quotient. That's what you get. Okay, so again, why did I introduce the natural log? I can't just bring the 2 over x down in front, right? If you have x squared, that's not the same as 2x. You can't just bring down the power because you want to. But when you put log out front, a log property says log of base to the power, you can bring the power down. Okay, now let's see what we have here. When x approaches 0, the denominator goes to 0. This is e to the 0, which is 1, plus 0 is 1. And natural log of 1 is 0. So now we have a 0 over 0 form. Okay, we didn't have it there, but once I took log of both sides and did this manipulation, now I have a 0 over 0. I'm taking the limit of a function with a 0 over 0 indeterminate form. So I can use L'Hopital's rule now. Notice I keep rewriting the left-hand side. We're not doing anything with that. But by L'Hopital's rule, the limit of this is the limit of the derivative of the top over derivative of the bottom. Now the derivative of x is 1, that's easy. And the 2 you can just bring down. Now what's the derivative of natural log of stuff? It's 1 over the stuff. Chain rule says then times the derivative of the stuff, which is e to the x plus 1. All right, let me check myself. So the derivative of x is 1. The derivative of 2 times a function, you can bring the 2 down. The derivative of natural log of stuff is 1 over the stuff times the derivative of the stuff. So let me write this pretty. So I have natural log of y is the limit as x approaches 0 from the right of 2 times e to the x plus 1 over e to the x plus x. Right, so write this as a fraction. That's the numerator, that's the denominator, and I just put the 2 with the numerator. Should we take the derivative again and use L'Hopital's rule, take the derivative over the derivative again? No, you can't do that here because notice when x goes to 0, the denominator, e to the 0 is 1 plus 0 is 1. The denominator, you're getting the limit is 1. So it's not a 0 over 0 or infinity over infinity. But now, to take the limit, you just plug in. Right? When x goes to 0, like I said, e to the 0 is 1 plus 0 is 1. So I get 1. And in the numerator, e to the 0 is 1. 1 plus 1 is 2. 2 times 2 is 4. Okay? So again, you can't, every time you use L'Hopital's rule, you have to stop and ask yourself, can I use it again? So we could use it to go from here to here because we had a 0 over 0 form. You can't use it here because it's not 0 over 0 infinity or infinity over infinity. Right? So notice what we have is natural log of y is 4. I called y the limit. Right? I called the limit we're trying to find y. So we just need to solve for y. Well, it's a log equation. How do you undo natural logs? You take e to the both sides power, and y is e to the 4th. So that's your answer. That limit turns out to be e to the 4th. So that's a little heavy-duty example there, but I mean, it's a procedure you should remember. If you're taking the limit of variables to the variables, call the limit something, y, take log of both sides, so then you can get that expression with the variable out of the exponent and make it a product. And you may or may not use L'Hopital's rule, but the point is, that's a procedure you can use to handle limits of variables to variables. Okay, so that's all about L'Hopital's rule.